This video is going to show how to visualize high-dimensional data with RPM Map. Let's first open our sample dataset with VSU Map. The sample dataset forms a simple sphere surface from a three-dimensional space. We can image that this dataset represents the Earth's surface without geographic features. We notice that the sphere displayed here only shows half of sphere clearly in the foreground. The other half is only vaguely visible in the background. A point in the map represents a data point. Since these points can have different shapes and colors, we will call them glyphs. We can view the 3D coordinators of glyphs through the context menu. We notice that each data point has an identifier, and a type that determines the color and shape of the glyph. Now, let's create a RPM map for our data set. We first duplicate our sphere map into a second map to avoid overwriting the sphere map. Then, we open the RPM mapping control panel. The control panel allows us to change settings for the learning algorithm. We can access more detailed parameters through the configuration button. But here, we just accept the default settings, and start the learning process by clicking the Start button. The map in the main window shows how the algorithm gradually creates a RPM map by simulating a multi-particle dynamic system. After the learning process has finished, we can then investigate our data in the main window. The map in the main window can be either in editing mode or shifting mode. The tool button here indicates that the map is in editing mode. Let's first switch the map into shifting mode and shift the map to a better position. We notice that the shifting operation works cyclically, that means what gets shifted out from the left side comes back from right side. And what goes out from the top comes back from the bottom. Then we switch the map to editing mode. In this mode, we can for instance, view the identifiers of selected data points, or change the shapes of some glyphs. We can reverse the changes through the Undo button. We can also configure the map through the property window. For instance, we can switch to a different glyph set. We can change the name of the map. Or the background color of the map. We can easily see in this map that the positions of some data points are slightly more irregular compared to other data points. This irregularity is not a product of the mapping algorithm, but it is present in the original data. We can verify this easily with a PCA view that is able to display data in a simulated 3D view. The RPM map therefore revealed us some irregularity in the data. We notice that this RPM map actually contains two round disks. One is located in the center, the other one is split into 4 pieces and displayed on the 4 corners. One way to show the 2 disks in one map is tiling multiple RPM maps to create a map that visually has no boundary. Another way to show the 2 disks in one map is using the diagonal rotation. In order to do so, we first shift these 2 disks away from the indicated diagonal lines. Then perform the diagonal rotation. We see that the 2 disks show a complete map of the sphere surface. A very useful feature of VSU Map is the filter object that enables us to scale data columns with different weights. We can create a filter for a map through its property window. As an example, We create a filter here that scales the data in the first column with double of its original weight. We can recreate our RPM to see the effect of the filter. But, here we just quickly show effect through the PCA view. We see that the filter has changed our data set from a sphere to an ellipsoid. Now, we are going to talk about the metric concept. A metric in Visu map is a function that measures the dissimilarity between data points. That means, different metrics characterize purposes of different analysis. A mapping algorithm in Visu map basically tries to create a glyph map to visualize the dissimilarity with proximity. By default, Visu map uses the Euclidean distance as metric to measure the dissimilarity. We can easily change the metric through the map property window. For instance, here we change the metric to the correlation metric. Then, we recreate the map with the new metric. We see that our map with the new metric has a simple linear structure. A segment on the straight line corresponds to a ring on the sphere representation of our data set.